Good morning, everyone. We're just going to wait maybe about one more minute or two just to make sure that everyone has a chance to come in, and then we'll make a start. So this will be for Year 8, the 9I topic, Forces and Motion. Today we're going to be covering kind of like 2 lessons in one go, but we should have enough time for that. Forces and a little bit of energy. Okay, let's make a start. Right. So our very first learning objective that we want to cover in this topic, and this is the start of the new topic now, is basically what is a force? Because this entire sort of section, the 9I topic, forces and motion, it revolves around this term force. And you guys have done this before in year 7. You've talked about what a force was. You had a topic about forces. But it is important that we properly define it. So if I were to ask you what is a force, you'd be able to tell me. So we're going to establish a proper definition for a force. And also, because we can measure forces, we need to know what units forces are measured in. And we also want to know some different examples of forces. And remember, like I said, because you've done some of this in year 7 already, you guys would be coming in with hopefully a lot of background knowledge to help with this. And hopefully then this little section here should just be revision. But if you forgot everything from year 7, that's completely fine as well, because I'm going to be going from scratch. Okay? So just to start off with, the definition of what a force is. Now, the definition of a force, it is really, really vague. You're going to look at it and think, well, that covers pretty much a lot of things. And that is true, because with forces, it's nothing specific. There are specific forces underneath this, but in general, a force is a push or a pull. Whenever you see a scenario where there's a push or a pull, that is a force happening. And then we're going to go into more detail about this in all of our examples of different types of forces, so you can see why we have this very broad definition of a force being just a push or a pull. And we have a unit of measurement that we can measure forces in. We measure them in newtons. And then we shorten newtons to N. We have this unit of measurement. It's named after this guy named Sir Isaac Newton, who was pretty much one of the biggest prides of the UK in terms of the scientific advancement of humanity. Basically, Isaac Newton came up with a lot, and he's done a lot in terms of setting out all of the laws, all the calculations when it comes to calculating for forces. So we've named this unit after him. And forces would then be measured in newtons. Say we, push a pen with 10 newtons of force, or pull a table with 20 newtons of force. It is just a standard unit of measurement that we measure forces in. So we have this broad definition for what a force is. Now let's talk about some examples of a force. You guys probably now can even maybe possibly think of some examples of different forces. But we have a lot. There are a lot of different types of forces, and because there are a lot, we'd like to organize them into two main categories. We'd like to organize them into either being contact forces or non-contact forces. Now just have a think about those two key phrases, contact forces and non-contact forces. If you don't overthink this, you can probably even already guess what the difference is between the two just from the name, contact or non-contact. In the case of contact forces, objects need to be touching. For the force to act. So basically, like for example, with the force friction, yeah, which comes from two objects rubbing together. You're not going to get friction if the two objects are away from each other. You're not going to get friction there. Like you won't have friction between yourself and your computer monitor screen because you're not touching it. So that force won't be around if there is no actual contact in place. But the second you touch it, then you can have a force of friction. So with contact forces, the objects need to be touching. But there are some forces where the objects don't need to be touching for there to still be a force that is felt. And we call these non-contact forces. So objects don't need to be touching. And we'll give some examples now, just for you guys to have a think about it. So, contact. We'll start off with the non-contact forces actually, because there's fewer of them. Let me change colors. What color do I want? We'll go with rose. Okay. Let's go with non-contact to start with. Just for you guys to understand about the concept of forces not needing contact. So imagine the first one. Imagine you jump up off the ground. You're no longer touching the floor, you're no longer touching earth, but you still fall back down on the ground, even though there's no touching between you and earth. So weight, I'm also going to put in brackets with gravity, because weight is essentially the pull of gravity on you. That is a non-contact force. If gravity if gravity was a contact force, if weight was a contact force, the second you leap up off the ground, you'll no longer feel gravity, and then you'll just be floating off into the distance. But because it's a non-contact force that doesn't require actual physical touching involved, it's still acting even if you're not touching. So weight, which is basically just the force of gravity on you, is a non-contact force. Another example of a non-contact force is magnetism. So like when you have two magnets and you're holding them together, but you yourself are like holding them, but you're not letting them touch, you still feel that pull between the two magnets, even across that little tiny, even across space. So even when the magnets aren't touching, there's still that pull towards each other. Remember, force being a push or a pull, and if you flip the magnet around to make them repel each other, you also feel the force, even when they're not touching, that force of repulsion to push them away from each other. So those are the two main non-contact forces that don't require touching. Now we'll move on to the contact forces. So these are not like every single force in existence. These are just examples that these are common examples that you sort of would have to know. So, oh yeah, and in the same case with magnetism, we also have like electrostatic, like for example, charges attracting or repelling. But you don't have to worry about electrostatic too much until GCSE level. Okay, now contact forces. Now if we think about all the forces that require some form of contact for it to work, basically. So we already talked about one earlier, friction, which is two objects rubbing. We have air resistance, which you can think of like friction, but with air. It's just like, all around you is air. It's not just empty space, even though you can't see anything and it looks like empty space. So when you are moving along, there's contact between the air particles and you that creates this air resistance force. Same goes for if you are in a liquid and we have water resistance. Same thing. The particles of the water, if you're swimming along, they push back against you, and we're in contact with that water, so it's considered a contact force. There's also going to be upthrust, which is something we talked about in Year 8 before, which is force that pushes up in a liquid that allows you to float. So like, let's say that we had some water and we had an object in the water. Well, weight is pulling the object down, but upthrust is pushing the object up, which allows it to float. So we also have upthrust. We also have tension. So like for example with a stretch spring, if something is like, if an object is pulled or stretched, it exerts a force on whatever's pulling on it. So example, stretched spring. Let me draw out this example. So let's say that there was a spring and we had like a 1 kilo mass that's pulling on the spring. Well, the spring is also exerting a bit of tension, trying to keep that object up. So that is this tension force there. And you would be able to feel the tension force with like anything that is stretched. Like for example, if you have like a hair tie, and you were to stretch it out, you would feel the force of the hair tie try to resist that and pull it back. So like when it comes to stretchable objects, when you sort of overstretch it, yeah, so tension is like elastic. Tension is like, but elastic, we consider that as a form of energy storage. Tension is the actual force due to the elasticity. So tension is the force specifically. So, let me... Okay, and there's one last one. Actually, two last ones. We also have thrust, which is like a driving force, basically. So like forces from the engine, essentially, whether you have a car or a rocket, whatever the case, a force propelling it forward. And there is one last force that I wanted to go over, because this is a force that everybody forgets about. That is the most commonly forgotten about force. And just to highlight the reason why you shouldn't forget it, there's the ground and here is you. You are standing still on the ground. Right. Let's have a think about what forces are acting on you when you are just standing still, standing on the ground. Well, there's obviously weight, right, keeping you down. But there is another force that's acting on you. It's not going to be air resistance because you're not moving about, not water resistance. There's no friction because you're not moving. Friction happens due to like two objects sliding or rubbing past each other. No upthrust, you're not in water. No tension really. There's no stretched objects here. No thrust. You're not like, you're not in a car or anything like that. No magnetism, no electrostatic force. But there is one other force. Now have a think. Let's pretend that we are saying, okay, there's only weight acting on you then. Well, if weight was the only force acting on you, why aren't you just crashing through the ground all the way until you reach the center of the earth, if gravity was the only thing involved here? If gravity was the only thing involved, gravity would be the only thing pulling on you. Therefore, it would just continuously pull you down and down and down until you reach the center of the earth. So, there must be another force involved that balances the weight, that balances the force that you are putting on the ground due to the weight. And this force is pushing upwards. And we call this the reaction force. Basically, yes, spot on, Max, the force of the floor pushing back up. So you are pushing on the ground due to your weight, but there is the reaction of the floor pushing you back up that prevents you from just crashing through into the Earth's core. And every single, we forget about this force quite a bit. It's the most easily forgotten about force because it's just there as a reaction to something. And this force, though, is really, really important because it prevents a lot of things from just going into one direction. It is the opposition to gravity in a way. Now, another way you can think of for this reaction force is that this reaction force will increase the more force you put on the opposite direction. So, for example, a lighter person, someone who only weighs, let's say, 300 newtons, that's 30 kilograms. Its reaction force will balance out at 300 newtons. If someone was 1,000 newtons, the reaction force would also be 1,000 newtons. So the reaction force also changes depending on what you can think of like the action force is. Another way you can see reaction force, and don't hurt yourself doing it, and don't break any furniture doing it, but if you gently tap the table, you feel the force of the table on your hand at the same time as you are putting a force on the table. If you lightly tap it, you feel that force. If you smack the table harder, then your hand is going to start hurting because of that reaction force from the table onto you is going to be larger in response to the force you put on it. So that's why we call this the reaction force, because the size of it changes depending on the quote-unquote action. Right, so our first learning objective, we've defined a force, we know its unit of measurement is in newtons, and we also talked about some examples of different forces. Don't worry too much about needing to memorize all of these. It is literally just purely having a think and being familiar with all the different force names. I'll I'll circle the most common ones that are going to come up regularly, just for you to be able to, when you see it in a question, not get confused. So weight is a force that comes up regularly in examples. Magnetism and electrostatic forces, not so much. Friction comes up quite a bit. Air and water resistance. Upthrust, not so much, but this is kind of, so I'm going to just underline it. Tension, not so much. Thrust comes up a lot, and reaction force is one that you have to remember exists. So obviously the ideal is for you to know all of these, but if you're feeling at all overwhelmed and thinking, oh my gosh, there's so many forces to remember, as long as you have it in your head, the main ones, and at the back of your head, the ones that are a bit more obscure, that only come up every now and again, I'm fine with that. Okay, so before we start on learning objective 2, well, I should say leading up to learning objective 2, let's imagine that there was a car. Here's my car driving along. Okay, so it's moving forward. So let's pretend that this car is moving forwards. Now let's think about all of the different forces that are acting on this car. Well, we just mentioned the car has a bit of weight, right? And in order for the car not to be crashing down through the center of the earth, to balance that out, we also have the reaction from the ground pushing the car back up. It's moving, so we also have thrust moving it forward. Now, what else would there be? Let's have a think. I'll give you a little bit of time just to have a think about what other forces are acting on this moving car. There's two more that I want you to know. Two more forces here involved. Okay, so that should be enough time for you to have had a little think. So the car is moving forward. There's going to be a force of friction between the tires and the ground. And I have the arrow drawn this way because the friction's trying to pull it back. It's going in the opposite direction to where the car is moving. And we also have another resistive force pushing it back, air resistance. Now, looking at this diagram, you can already tell, wow, with something as simple as a moving object, there's a bunch of forces that are acting on it. So, let me tell you one thing. Us physicists are lazy. I mean, we're constantly modeling things as circles or boxes. We don't like drawing things out. I mean, this little car here is the best I could do. So when we see that we have 5 forces that are acting on this object that we have to do calculations for, we don't want to do calculations for every single one of these forces. I mean, that'd be too much. So what physicists have come up with is we've thought about, can we sum up these forces all together and just use one overall force to represent all of the forces that are acting on the object? So summarize all the forces acting on the object with just one overall force. Well, that's what we did. We called this the resultant force. And I'll give you some examples of a resultant force and how to find it in a second. So the resultant force is basically the overall force acting on an object. And its unit, because it is a force, all forces are measured in newtons. And if you think about the word resultant, it's similar to result, right? So it's like after everything, what is the result? What is the resulting force? But we call it the resultant force. So here's an example. Let's put numbers to this. Let's say that same car. Okay, I'm going to put a little bit of numbers on this with different colors so you can clearly see. We'll go with blue. So let's say that the thrust, I'm just making up these numbers now, thrust is 100 newtons. Let's say the weight is 1,000 newtons. That means the reaction force is also going to be 1,000 newtons. Let's say that the friction is small, 20 newtons. Oh, I drew this arrow a little bit too big. Hold on, let me redraw the arrow because it's bothering me now. Redraw that arrow. I'm going to do it less. Okay, we'll go with that. Okay, let's say that friction is 20 newtons and air resistance is also 20 newtons. So those are all my numbers. Thrust 100, weight and reaction 1,000, air resistance and friction are both 20 each. And I wanted to calculate the resultant force on this. This is a lot easier than you think, so please don't look at all these numbers and feel overwhelmed. Reaction and weight are both 1,000 and they're going in opposite directions to each other. So we can think of them as canceling each other out, basically. So I'm going to draw an X to say we cancel it out. There's 100 newtons pushing the car forwards from its thrust, 20 newtons from air resistance pulling it back, and 20 newtons from friction pulling it back. So you can think of it like there's an overall 40 newtons pulling it back. So 100 newtons pulling it forward, 40 newtons pulling it back. The resultant force is 60 newtons forward. And that is the resultant force. So basically what we've done is instead of needing to look at every single one of the forces, we've decided, okay, let's sum up what's happening here with an overall force. Now I'm just going to quickly put a little bit of resultant force practice for you guys. It'll just be quick. Oops. Here we go. Right. So I'll give, say, 5 minutes for this. 5 minutes for this. There's 5 different smiley faces here. So it's not like all of them in one. So for each of them, I want you to try to find the resultant force. So we'll label these question number, oops, where's my pen? Oh, there it is. Question number 1, 2, 3, 4, 5. So find the resultant force of each of these scenarios. And remember, you want a number, the unit, newtons, and then I also want you to draw an arrow to show what direction that force is going to be acting in. And then we'll give 5 minutes, so at 10:35, I'm going to give the answers to these to check that you have managed to find the resultant force for each of these. Actually, this shouldn't take you as much time. We'll say 3 minutes. 10:32. Okay, let's go over some of the answers. So I'm going to start with the leftmost one. There's 35 newtons up, 35 newtons down. The resultant force is just 0 newtons. 35 newtons to the left, 20 newtons to the right. The resultant force, it is just 15 newtons to the left. 8 newtons to the left, 6 newtons to the right. We have 2 newtons to the left. With this one, 40 up, 38 down, 2 newtons up. And then the 10 and 10 cancel. We're left with 15 and 5. It'll be 10 newtons left. So those are the resultant forces for each of those scenarios. Basically, all we're doing is essentially like any forces that are acting on opposite direction, we cancel out what we can and see what we're left with as the result. That's what the resultant force is. Okay. Now, what does this have to do with motion? And using this to predict how an object is going to move. With resultant forces, we can use the resultant force to do calculations. Calculations will be at GCSE level, but I'm just giving you basically an idea of what the point of finding the resultant force is. In terms of it's an object's motion. So right now at your level, I just want you to understand the concept. So then when you're doing your GCSEs, you understand the concept. Now you're just going to be adding the calculations level to it. So when it comes to predicting an object's motion due to its resultant force, we have two new keywords. Balanced forces versus unbalanced forces. And depending on whether these forces are the forces acting on an object are balanced or unbalanced, that will change. That will, like, the object's motion will change depending on it. So when forces are balanced, like in the first question, the first smiley face, when everything is balanced, the resultant force is 0. So basically, balanced forces are essentially just when all of the forces that are acting on an object balance each other out and you get a resultant force of 0. Now, let's take this to real life then. Let's pretend that you're playing tug of rope with somebody else. You're pulling. There's you two pulling on the rope. There's a flag in the middle, isn't there? Let's say that you're pulling on the rope with 10 newtons. Your friend is pulling on the rope with 10 newtons. These forces are balanced, right? They cancel each other out because they're the same force, just acting in opposite directions. So they balance out. The resultant force in this scenario is going to be 0. Think about the actual rope then. Is the rope going to go in any particular direction? Is it going to start moving? Well, it's not, right? Because there's no force that has won out. So, in the case of balanced forces, there is no change to objects' motion. If it's stationary, it's going to stay still. Like for example, let's look at anything on a table near you. Let's look at a pen that's on the table. You might think, well, there's no forces that are acting on the pen because nothing's happening to it, but there are plenty of forces. For example, there's a weight force, there's a reaction force. They've just balanced each other out so that you don't see a change to the object's motion because the resultant force is 0. However, one thing that I also want to point out, and why I've said no change to object's motion instead of just saying the object is still, the reason why I say that is because if the object is already moving and the forces are balanced, there is still going to be no change to its motion. So let's say that a car is already moving. There's my car. It's already moving. We have the thrust force is 100 newtons. And then let's say the combination of friction and air resistance, let's say it's 50 newtons each. 50 newtons of air resistance, 50 newtons of friction. They're balanced, right? Because there's a sum total of 100 newtons of resistance moving to the, like, pulling it back, a total of 100 newtons pushing it forward. The resultant force, I'll say RF, is 0 in this case. But the car is already moving. So what happens is when you see balance forces on an object that is already in motion, it's just going to stay at the same speed. So it's not going to all of a sudden stop and stay still. It's going to move exactly how it has been moving. So when it comes to balance forces, if the object wasn't moving in the first place, that's not going to change. It's staying stationary. If the object was already moving, it's going to stay how it is. Basically, having a resultant force of 0 just means that there's going to be no change to what it's already doing. Now, if we have a resultant force that is not 0, so I'm going to put resultant force is not equal to 0, as in there is going to be an overall force that's acting in a particular direction. There is going to be a change in object's motion. So it's either going to speed up or slow down. And when an object starts moving, it's speeding up, right? Because it's going from 0 to whatever its new speed is. So it's either going to increase in its speed or it's going to slow down. Now here's another common mistake a lot of students make. Let's pretend that we have our car again. We start off at this constant speed here of thrust being 100 and all of the resistive forces also being 100. It's moving at constant speed because its forces are balanced. Its motion is not changing. Now let's pretend that the driver of this car decides to lower the thrust a little bit. Let's say it lowers to 80 newtons of thrust. And air resistance and friction were still the same at the very start. So he lowered the thrust to 80, and then the air resistance and the friction were still the same immediately after he did that. Well, we have a total of 100 newtons pulling it back, 80 newtons pulling it forward. So overall, the resultant force is going to be 20 newtons to the left, right? But that does not mean that the car's gonna all of a sudden start moving backwards. What this means is that there's just a change to the object's motion. It's either speeding up or slowing down. In this case, it's gonna be slowing down. And I'm gonna take a quick pause to re-explain this because I know that this section here, a lot of students get confused by it. A lot of students make a lot of the same common misconceptions. And the reason why they make it is just because the definitions are not clear. So, with balanced forces, when the resultant force is 0, there is no change to motion. That's the key bit that you have to remember, that whatever it's doing, it's going to keep doing exactly the same. When there's an unbalanced force, there is going to be a change in the object's motion, meaning it's either going to speed up or it's going to slow down. It's in a particular direction, obviously. So if it was stationary, it's going to speed up in whatever direction one out. But if it's already in motion, it's either going to speed up faster or slow down. And it does not mean it's moving backwards. So when it comes to an object in motion, do not think of it as the arrows pointing into the direction it's going to go. The arrows just represent the force. And so when it comes to an object that's already in motion, you do have to be very, very careful and not assume that it's just going to move in the direction of the arrows. It might not do. It'll either speed up or slow down. So I was going to do the energy bits, but I think I don't want to take too long and start running out of time. I do want to give you guys time to practice. So I'm going to link, so we're finishing now, Florence. So I'm going to link you guys quickly to some forces practice. Here you go. It should also be on the website, so if that doesn't work, that link doesn't work, I'm not sure if it will. Oops, hold on. There we go. If you scroll down to the force and motion topic, you should see it in there, in that folder. And you should see two sheets in there, the Grand Prix Answers and Grand Prix Race. So this sheet shouldn't take you very, very long. And once again, this is optional work, but I do have the answers on there for you. So if you feel like, you can develop a little bit of confidence to make sure that you're on the right track with this forces stuff. Basically, the sheet, the Grand Prix Race 1, that sheet is going to be the actual worksheet. And then I have the answers on the left for you to check out yourself. So just make sure that, don't jump to the answers straight away, because there's no point in that. You're not submitting this in to me. This is just for you and for you to feel like confident in the forces topic a bit. So use the answer sheet only after you've done it to check yourself. And if there are any answers on that sheet where you feel like, hang on, I don't really understand where that answer came from, and you need me to re-explain it, feel free to send me an email or leave me a comment on Show My Homework. That's absolutely fine. Okay? So we'll leave it at that because I don't want to exceed the hour, and I also want you guys to have enough time to get the work done. Okay? So that was it for the forces. We're going to pick up again tomorrow with a little bit of the energy topic, and hopefully we'll get to a little bit of doing speed calculations as well, but we'll see how much time we have. All right. See you guys. Have the good rest of the day, and once again, let me know via email if there's any of the questions that you feel like you don't really understand where I got my answer from, and I'll be sure to get back to you. Okay, bye guys.